In this video, we're going to go over how to calculate the midpoint Riemann sum of a curve between that curve and the x-axis over an interval. So this says use a midpoint Riemann sum with 4 equal subintervals, remember that means n equals 4, to approximate the area between f of x equals root x and the x-axis over the interval 0 to 4. Remember that that represents a and b. So this is much like the left and right Riemann sums. If you haven't watched those videos, or that video I should say, please watch that first. It'll explain a lot of what's going on here. So this is just another way of approximating the area from 0 to 4. And I keep using the same curve so you're able to compare the similarities and differences between what we're doing. So we know that we've got 4 subintervals from 0 to 4. So 0 to 4, if we find delta x, the width of each rectangle, that's going to be b minus a over n, where b is that n.4. A, we know, in this case is 0, right, that starting point, all over the 4 subintervals we're going to slice this into, and that's going to be equal to 4 over 4, which is 1. So we get the same exact delta x as we did in the previous video. So these are our subintervals here. Now the difference between this and a left or right Riemann sum is only in where you get the heights of your rectangles. That's it. So instead of going to the left-hand part to get your heights, 0, 1, 2, and 3, or the right hand, 1, 2, 3, and 4, we're going to now rely on the middle to get our height of our rectangle. So between 0 and 1 on that width, still 0 to 1, the height is going to be at 0.5. That's it. And that gives you the height of your rectangle. So you go out from there and that gives you your rectangle right there. So the very first rectangle's area is going to be a width of 1 and a height of f of 0.5. So that'll be a width of 1, that's your base, times, and I usually do f of x times delta x. So the height of the rectangle, f of 0.5 times 1. Same exact width, different height. Next, we're going to take the midpoint from 1 to 2. Well, that's at 1.5. So the height of the rectangle will come from 1.5. Ah, very sweet. And so the height will be f of 1.5, the middle point, times a width of 1. That's delta x. I'm just kind of doing it right out. Remember, we're doing height times the width. Then here, the midpoint's going to be at 2.5, so the height will come from right here. Notice that we're getting a little bit over the area and a little bit under the area, right? So a little bit over, a little bit under. And so that will be f of 2.5, nice, times 1, a width of 1. And last but not least, the midpoint here is 3.5. So the height will come from f of 3.5. Ugh. So those are going to be some nasty numbers on the calculator, that's for sure, but we get calculators for that. And that's it. So that's going to be f of 3.5, right? That is the height of this rectangle, that height, times the width of 1. Okay, so done out, this would be, well, where do we get our heights from? The function. So this would be the square root of 0.5 times 1. And I'm going to show you this now. We could factor out delta x from everything and just add up f of each of those values. So it'd be the square root of 1.5 plus the square root of 2.5 plus the square root of 3.5. And that would give you the midpoint approximation. When I come back, I'm going to freeze the video for a quick second, do some terrible video editing, and then come back with the approximation. And there you go. I promised some terrible video editing, but here we go. The approximation for this value is going to be 5.384 if you round up. 5.384, which is interesting because if you remember from a previous video, we got the left-hand approximation was like 4.146. That's lower than this. And the over approximation, the right-hand sum, was 6.146. So that went over this. Is this the exact value? No, it's not, because we don't have a straight line here. So it's not like the same is above as the same that is below the curve. But it gives you a pretty darn good approximation. That's it. That's a midpoint Riemann sum approximation. It's excellent. It just uses the middle of every subinterval. In this next video after this, I'm going to go over trapezoidal approximations. Instead of using rectangles, we'll use trapezoids. We'll see you there.